Okay, so in the last lecture we had introduced the notion of a topological vector space. So let me first recall what we had discussed. So let X be a vector space, right? Let X be a vector space and tau be a topology on it. Tau be a topology on it. Then X with respect to tau, which is already a topological space. So this is called a topological vector space precisely. If so, we required it to satisfy two conditions, right, in order for the topology and the vector space operations to interlink between them. So all the single points, or rather I can simply, by points I mean single points, right? So all points of X are closed, that is something which we require, or rather closed sets, and the vector space operations, the vector space operations are continuous with respect to tau. Got it? That is, these are the two conditions which we require, right? And we had given an equivalent definition for these operations being continuous. Let us also recall that as well. So we had said that number one, that so what it should mean to be continuous. The usual definition of continuity which comes from topology is that a function between two topological spaces is said to be continuous if the inverse image of any open set in the codomain topology is also open in the domain topology, right? That is the usual definition. So we'll obviously abide by that definition itself. So, and see, in the domain, in this case, when we are considering the additive operation, the domain becomes a product topology, because we have a direct product of the vector space with itself, right? I am taking a coordinate x y and I am mapping it to x plus y. So I am choosing elements from v cross v and I am mapping it to v, right? So whenever I am taking the inverse image, it must correspond to inverse images partly in the first copy of the direct product and the second copy of the direct product. I need to keep that in mind, right? So if x1 x2 are elements from x and v is a neighborhood of x1 plus x2, right, then now I am having the map from x cross x to x, right, because x is the vector space I am starting with. Therefore, V is an open set containing x1 plus x2 in capital X. So, it is in the codomain set. So, I need to take the inverse image of it, right. So, by taking the inverse image, since I am saying it is continuous, so by taking the inverse image, I will get a neighborhood of x1 in first copy of x, I will get a neighborhood of x2 in the second copy of x, and I can add them up to get the inverse image of the neighborhoods of x1 and x2 in x cross x, right. So, then there exists neighborhoods v1 and v2 of x1 and x2 respectively, such that v1 plus v2 is contained in V, right. A simplest observation of saying that it is continuous. Got it? Okay, fine. And we also had an analogous definition for the scalar multiplication to be continuous as well. So recall what we had said, that if x is an element from capital X and alpha is a scalar value, v is some neighborhood of x. Sorry, I need to take hold of neighborhood in the domain set, right? So it's of alpha x, then for some r in r greater than 0, some neighborhood w of x beta w must be completely contained in V, whenever beta minus alpha is less than r, right? So these were the equivalent definitions we had in case of the operations x1 plus x2 and x alpha x1 or alpha x arbitrary for an arbitrary number x in the from the vector space capital X to be continuous, right? Okay. Now we define what a bounded set is. Now we know that the usual notion of a bounded set in any arbitrary Euclidean space or let's say a topological space itself is that a set is said to be bounded if I have it restricted within a bigger ball, right? That's the usual notion. That is, suppose I have a set like this X, then I'll always get balls like this within which X is entirely confined, and if I go beyond these balls as well, every other ball will completely contain X within itself, right? So I can keep constructing these balls bigger and bigger, but X will still be entirely contained within all these balls. Okay, so this is the other way of saying that X is completely confined, completely restricted within a ball of a certain size, and that's in some sense the smallest ball which entirely contains it. If I go beyond that ball, beyond the radius of that ball, X will still be entirely contained inside. Okay, so an analogous definition will hold as well. That sorry, yeah. So a subset of the topological vector space X is said to be bounded. Is said to be bounded if for all neighborhood V of the origin, so I am writing it as a vector, neighborhood V of the origin in X, there exists some s greater than 0 such that E is completely contained within the set T V for all t greater than s. Okay, so what's it trying to say? Let us quickly construct an example to some sort of understand what it's trying to say. Let's say suppose V is the neighborhood around the origin of radius, let's say 1. Okay, so let me draw it in the Euclidean plane. So what I have is that V is this disk, right? So V is this disk, open disk. Obviously I'm talking about open disk. So yeah, okay, let's fine let it be like this only, it won't cause any problem. So suppose this is my V, right, and I have a set E which I am trying to define to be bounded. So let's say E is let's say E is somewhere here. Let's say suppose this is my E. Okay, what is it's trying to saying is that I have some real number, some positive real number S, such that whenever I scale this neighborhood V by T. Now what does T V with our conventional definition means, which we did in the previous lecture? So it is the collection of all the points Tx such that X was already in V, right? Now if a set was already in V, recall by definition of V, so its modulus is less than 1 or less than equal to 1, whatever, but its modulus less than 1. So if I, so what are the distances of these values Tx from origin? So this should be mod of T times mod of X, right? So this is less than mod of T, right? So this what is this actually doing? It is just scaling the ball by some multiple of T, right? T will surely be positive number, so this can be written as T. So I am just scaling the ball of radius 1 around 0 by a multiple of T, and what I am trying to say is that when I cross some fixed positive real number S, then every ball will contain this E entirely inside it. Okay, so suppose let's say this is S. Okay, this is S greater than 0. So if I consider T exactly to be equal to S, so I'll get a ball some sort of like this, right? It is not still entirely containing E, but as I exceed S, I'll get a ball like this which will completely contain E, and if I go beyond it, all the other balls will still contain E, right? All the other balls will still contain E. Okay. So this is the our usual notation of being bounded, and it some sort of abides by your intuitive geometrical guessing of how a bounded set should look, right? Or we can in fact also think of it in some sense that a set is said to be bounded if there exists some positive real number such that when I construct the ball of radius that real number around origin, this set will be completely contained inside that inside that ball. Okay, because if I claim that E is completely confined, completely contained inside ball of a certain radius around origin, then if I just keep on increasing the radius, I'll get a bigger and bigger ball, and E will be, symmetrically will be inside that ball, right? So this can be some sort of a very lame sort of a thinking, but this is quite, what should I say? This is quite um, appropriate in order to just remember sort of the definition of being bounded. But I guess it's sort of very simple to observe. Okay, clear? Now we want to define, so what we are actually doing in the previous lecture, in this lecture itself, we are actually setting up definitions and notations which will be explored later after we gain some sort of tools in order to tackle things. Okay, and we'll obviously observe that these notions and definitions are something on which the entire course will be dependent upon. Okay, so definition, let x tau be a topological vector space. So this will be the abbreviation I'll use. Associate to each a in x and to each lambda non-zero scalar quantity or rather I should say operators which we denote as Ta and m lambda defined as follows. So how do we define it? So I consider this operator Ta from x to x. So what does this do? This takes an element so I have this, so it takes an element x and it maps it to a plus x. This will do. And m lambda from x to x, what does it do? It takes an element small x and it maps it to lambda times small x. Okay, so this is for all x in capital X. Okay, so what we are trying to do here is that, so carefully observe what we are doing here. We are choosing each vector from capital X and we are translating it by a factor of a, right? So what happening here is what we call a translation by a. And what's happening here is just a scaling by lambda. So again, if I go to the geometrical point of view, I can think of it in this way, that suppose this is my x. So every point I choose on x, I am just scaling it by lambda. So eventually it will remain the way it looks, but it will just be scaled by a. Okay, so this is my a plus x, and when I multiply it by lambda, for example, if lambda is positive, it will gain in length. So this will be lambda of a plus x, right? So what we are doing is that we are fixing a translational factor and we are fixing a scaling factor, and I am choosing each vector from the topological vector space. I am translating it by a, and considering this operator to be the translation by a, and I am scaling it by lambda and giving it also an operational an operator definition. Okay, so I am considering them to be operations, right? We can pretty trivially define what a translation and what a scaling looks like, but it's better if I give them a functional sort of a definition. Okay, then I can use it rigorously over and over. Okay, and immediately after this definition we will get a very important proposition which says that the operators Ta and m lambda are homeomorphisms. We can obviously talk about homeomorphisms because we have X endowed with a topology. The TA and M lambda are homeomorphisms of X onto X. A quick recall what a homeomorphism is. So, a homeomorphism is a bijective continuous map whose inverse is also continuous, right. So, homeomorphisms are specifically isomorphisms of topologies, right. For example, we have isomorphisms of groups, rings, fields, and we have isomorphisms of vector spaces in terms of linear transformations. So, isomorphisms or equivalence of topological spaces are some sort of homeomorphisms. Okay. So, let us quickly go to the proof of it, and the proof is quite simple because you can easily observe that first of all these are linear operators. So, they have the same domain and the same codomain set, but these are these are actually invertible as well, because if I just consider the scaling factor by 1 over lambda, because we have chosen lambda to be non-zero, and this is in fact the reason why we had chosen lambda to be non-zero, and if I choose the translational factor to be just minus a, then I can construct the inverse operations to these, right. Observe that firstly, now these are trivial observations, that firstly TA and M lambda are both injective, right. Because the field forms an integral domain, right. Sorry, I'm not working in a field here. I'm having X as a vector space. Yeah, recall I am having X as a vector space, and it's an additive abelian group, if you as a quick recall, right. So, all the group properties will hold here. So, the cancellation will also hold here trivially if you go for a quick recall, right. Yeah. Or rather, in some sense, you can actually observe this immediately that it's injective. There's no explanation needed as well, but you can just come up with this. And as injective and surjective as well, right. Why is it surjective? We will get to know from here. As observe, injectivity is pretty obvious. So why is it surjective? You can immediately look it from here. As observe that T of minus a, I mean the scaling, if I take the translational factor to be minus a, then this just acts as the inverse operation to TA, and if I have the scaling factor as 1 over lambda, then this acts as the inverse operation of M lambda. So, if I choose any element from X, I can consider this to be scaled by lambda and then rescaled by rescaled by 1 over lambda, right. So, every element in X will have a pre-image, right, under M lambda, and similarly under TA. Okay, got it. Now observe that moreover all these these 4 operators which we have, they are dependent only upon addition and scalar multiplication, and we know that additions and scalar multiplications are continuous in nature, right. Now observe that TA and M lambda are continuous by the definition of the topological vector space, right. Because when we had defined topological vector space, we had said that the addition of the vectors and the scalar multiplication of the vectors, they must be continuous. These operations must be continuous, right. So, they are continuous by the way they are defined. In fact, what we are getting here is that the inverse maps are also operators of the same type, and their inverses are operators of the same type, right, of the same type, hence are continuous as well, Thus, TA and M lambda are continuous maps, they are bijective, and their inverses are continuous as well. So, they are homeomorphisms, which implies TA and M lambda are homeomorphisms. Clear? Once we have come up with this fact that they are homeomorphisms, there is a very important conclusion which we can immediately draw from here. Okay, let me add a page. Okay. Thus, So we have established topological equivalence between the open sets of X with itself under the translational map as well as under the multiplication by scalar map, right? Therefore, if I take any open set from X, then via the translational map, which came out to be a homeomorphism, so E in X is open if and only if A plus E is open in X, right? And this will obviously happen for all A in X. Got it? Due to the homeomorphism of the translational map, right? This phenomenon is what we call translational invariance. Okay, this is called translational invariance. That is, an open set, I mean a subset is open if and only if its translation is open by its translation by some vector is open as well. Okay, got it? Okay. Now recall the definition of a local base. So how was the local base defined in terms of simply the topology? So it was defined as the collection of neighborhoods of a point such that every neighborhood of that point will contain some element from this collection, right? Recall a collection gamma of neighborhoods of a point P in X is said to be a local base. So it's a collection of neighborhoods, so it's a collection of open sets containing P, right? It's said to be a local base if every neighborhood of P contains a member of gamma, contains a member of gamma, right? Okay. So how is it useful in terms of translational invariance? So it you should remember this phenomenon. It will be used over and over again as well. Yeah, so whatever we are doing in these first two lectures will obviously be of use over and over again, because we need to classify topological vector spaces in terms of these things. Then we will eventually come up with some more deeper notions. For example, the maximum portions which we deal with are local notions. Okay, for example, here we have local base, so we are looking over a very small region to identify things about the whole topological space, and this translation somewhat helps us in doing that, right? Because if I talk about a very small open set, I can just translate it by some vector and I can place it in in any position in the topological vector space, and that will also be open, right? So this translational invariance actually helps us look over this topological vector space in a smaller in a very small area, because the scaling factor also came out to be a homeomorphism. So I can also scale up the open sets, I can translate these open sets, so I can roam about throughout the topological vector space having information about a very small area, right? So discussing about local notions, we'll eventually talk about global notions, right? So this is the definition of a local base. What I'm trying to say is that, so we can translate local bases to get hold of all the other open sets of X, right? Translate or scale, whatever you want to do, but talking about local things can eventually get us to talk about the other open sets in X, right? This actually speaks, so what I just said is quote unquote, this says that the topological the topology of a TVS, a topological vector space, can be completely determined by a local base, right? Okay, now I am arbitrarily using the term local base, but our definition contains that local base obviously depends upon a certain vector, but what is our central vector to always talk about in any case? The origin, right? So let me just set a convention that whenever I use the word a local base, I always mean local base at the origin. Okay, I always mean this whenever I use the term local base. Okay, if at some point I specifically mention local base at some vector P, then that's a separate issue, but whenever I talk about simply local base, I only mean the local base at origin. Okay. Okay. So for simplicity, we can just simply define what a local base, because we have specified that by local base we mean a local bit at 0. So this is just for simplicity, that a local base of a topological vector space X is a collection B of neighborhoods of the origin such that every neighborhood of the origin contains a member of B. Okay, so it simply abides by the definition of a local base at an arbitrary point. What we are doing is that we are just strictly restricting it to the origin itself. So let me just repeat: a local base of a topological vector space X is a collection B, script B, of neighborhoods of origin such that every neighborhood of origin contains a member of strip B. Okay. So one more point which we can immediately add is that the open sets of X are precisely those that are unions of translates, right, of members of P. Okay, so this somewhat it somewhat comes from the concept of a topology, because we know in a topology, given an open set, I can cover it using arbitrary union of open sets, but we have also given here the notion that any open set can be can be derived from a local base, right? So we have given a strict notation to the local base of our origin to be script B. So I just pick out members from script B, I translate it, I take their unions, and I can consider any arbitrary open set in X. I guess you can just visualize what's going on here, right? How are we trying to actually globalize a local notion? Got it? Now there is a very important property of the metric spaces which you had previously studied, I guess, which said that metrics are invariant, right? But the invariance of metrics, it has some sort of come up from this translational invariance itself. Okay, so recall, or rather not say recall, because I have not discussed it previously. So let me just define. Okay, a metric D on a vector space X is called invariant. So you need to keep in mind that we are considering a vector space. Is called an invariant metric. Is called an invariant metric if D of x plus a, y plus a is equal to D of xy for all x, y in X, a in X, right? Okay. Now why do we require a vector space? Because recall that whenever you have a metric, you can induce a topology using this metric, right? Metrics are ordinarily Hausdorff, and recall in a metric space you can talk about closedness of singletons, right? And talk about closedness of singletons. So in fact, given a metric, you can try and induce a topological vector space where the topology is compatible with the metric. We will talk more about this, that when is given a topological vector space, is it metrizable or the other way around? The other way around is sort of trivial, because given a metric, you can construct open balls, you can serve those collection of open balls to be a basis for a topology. This topology is somewhat induced by this metric, right? But the converse need not be true. Not all topological spaces are metrizable. This is something which you have surely done in some topological course. For example, the co-countable topology over a non-empty set, or let's consider the real set itself. The real Euclidean space with respect to the co-countable topology is not Hausdorff. Since it's not Hausdorff, it is not metrizable. So that can serve as an example. of a topological space which is not metrizable. All topological spaces are not obviously metrizable. All metric spaces are can be made into a topology. Rather, so we end this lecture with a collection of definitions which we will be exploring in the near future. Okay, so let x tau be a topological vector space, then A, x is said to be locally convex if there exists okay, let me erase this part. Okay, so x is said to be locally convex if there exists a local base script B whose members are convex, Number B, x is locally bounded if the origin has a bounded neighborhood. Okay, so you can obviously see we are all defining local properties of the already global properties which we know. Okay, because we have already seen that we can scale up properties which are homeomorphism, we can scale and translate properties to globalize it. So it enough to talk about local notions, right? X is locally compact. X is locally compact if so x is locally compact if the origin has a neighborhood whose closure is compact. Okay. Definition D, we say that a topological vector space is metrizable if there exists some metric on it, if we can define some metric on it which can induce the same topology. So x is metrizable if tau is compatible with some metric D on x. That is, I can construct a metric D on x, and using that metric I can form this topology, right? In that case I say that the topology is compatible with that metric. Okay, x is said to be an F space. This symbol F has come from the father of metric spaces, Fréchet. Okay, Fréchet had this notion of a metric spaces in his PhD thesis. I don't exactly remember, but I think it was that only. And I guess later Hausdorff published a book in which he popularized the notion of metric spaces, and that book was the first book to contain the notion of topology, which was introduced by him. So X is said to be an F space if tau is induced by some complete. Now we know that not all metric spaces are complete. By completeness I means that the Cauchy sequences in the metric space are convergent. Like we know that in any metric space convergent sequences are always Cauchy, but in an arbitrary metric space Cauchy sequences need not be convergent. Okay, if they are convergent in that very metric space, then we say that the metric space is Cauchy complete or simply complete. So it is induced by some complete invariant metric D. Okay, right, that is X is metrizable and this metric should be complete and invariant. X is said to be a Fréchet space. So Fréchet comes into existence. It's said to be a Fréchet space if X is locally convex. So what we had defined local convexity to be, recall. So a space is said to be locally convex if there exists a local base whose members are convex, right? Yeah. So X is said to be a Fréchet space if X is a locally convex F space. Okay, right? Now these are getting complicated and complicated, but with due time we'll get hold of each of these notions. We say that X is normable. So as the name suggests, it's normable if there exists a norm on X. Okay, if there exists a norm on X such that, now we know that norms induce metric, metrics induce topology. Now the other way around is true, that's a very usual notion. So once I have a norm, I need to link it with the topology which is already existing on this topological vector space. So this norm should be compatible with a metric, and the metric must be compatible with the topology. So X is normable if there exists a norm on X such that this norm induces a metric, induces a metric which is compatible with tau. And final definition is that X is said to have, now this is also important, X is said to have the Hein-Borel property. X is said to have the Hein-Borel property if every closed and bounded subset of X is compact, which we abbreviate as. Now I guess you guys already know what the Hein-Borel property is. It's a very elementary property which we use in real analysis as well as in metric spaces, so I'm not explaining that anymore. So these are the definitions which we will be eventually exploring in some lectures coming up to be, and in the next lecture we will set some properties which will also be proved in proved in due time, and slowly and steadily will, in the next lecture I guess, or in the next to next lecture, we will come up with the notion of separability. Okay, so meet you guys in the next lecture.